In the second set of slides, we'll see how the principle of maximum likelihood estimation is applied to the specific cases of the spatial lag and spatial error model. First, we'll look at the lag model, then we'll see briefly how the principle is applied to the spatial error model. A lot of this is very similar, and then finally we'll have some comments on model comparison. So first of all, maximum likelihood estimation for the spatial lag model. Now, why do we need this in the first place? If we look very closely at the reduced form of the spatial lag model, so we move the spatially lag dependent variable first to the left-hand side and then solve everything out by using the inverse of the matrix I minus rho W. And the result is y as a function of I minus rho W inverse times the x beta, the regression part, and then I minus rho W inverse times E, the error term. The problem here is that the spatial lag dependent variable, which is W times this expression, will contain the term W I minus rho W inverse E, the error term. And therefore, the spatially lag dependent variable will be correlated with the error term, which violates one of the basic regression assumptions, namely that the regressors need to be uncorrelated with the error term. And this is often called simultaneous equation bias. So the main estimation issue in the spatial lag model is how to deal with this simultaneous equation bias, how to deal with the endogeneity of the spatially lag dependent variable. The maximum likelihood approach goes about this by specifying a full distribution for the error terms. So we have our spatial lag specification. Y is a function of rho wy, the spatially lag dependent variable, x beta, the regressors, and E, the error term. So the way we go about this in maximum likelihood, we need to fully specify the distribution. Now the question is the distribution for what? And this is very important. The distribution is for the error terms. So we start by assuming joint multivariate normality of the error terms. And for simplicity's sake, here we do not allow heteroscedasticity. So in other words, the vector of error terms E, all the error terms in the data, follow a multivariate normal distribution with mean 0 and variance covariance matrix sigma squared, a scalar, times the identity matrix I. So this is an n by n multivariate distribution. So the approach in maximum likelihood is we specify the distribution, and that gives us the form for the likelihood function. So in general, for a multivariate normal distribution, the log likelihood is expressed for the joint density. For example, if E, the error vector, follows a multivariate distribution, normal distribution, with mean vector, everything is a vector, 0, and variance covariance matrix sigma. In general, then, for a multivariate normal problem, the log likelihood takes the expression that we have on the slide. So the first term, n over 2 times the log of 2 pi, is a constant, and we can safely ignore. In practice, it's important to know whether your software includes this constant in the computation of the log likelihood or ignores it. The value of the maximized log likelihood, which we will use in a likelihood ratio test statistic, will depend on that. So the first term is a constant, is of no particular consequence. The second term is 1 over 2 times the log of the determinant of the variance-covariance matrix. That's a standard result for multivariate normality. And the third term is 1 over 2 times a quadratic form of E prime sigma inverse E. So this is a quadratic form of the error vector in the inverse of the variance-covariance matrix. So in a standard situation, maximizing the log likelihood in this multivariate normal setting boils down to minimizing a weighted type of least squares, a weighted least squares of the multivariate normal vector E, weighted by the inverse of the variance-covariance matrix. Now, how do we translate this to the case for the spatial lag model? The spatial lag model, we need the likelihood for the dependent variable. The assumption of multivariate normality is for the error terms, but the error terms are not observed. They're just part of the mathematical construct that we have to have the regression model. So we need to go from our assumption of multivariate normality for the error terms to the distribution and then eventually the likelihood for the observed dependent variable y. And the way we think about this is as a form of variable transformation. So if you remember your mathematical statistics courses, you may remember problem sets where you're giving a random variable with a particular distribution, and then you have to derive the distribution of, say, the square root of that random variable or the log of that random variable. That's a variable transformation problem. Now, the spatial lag model is also a case of a variable transformation problem, namely if we think of it as expressed in terms of the error terms, then the error terms are a function of I minus rho w times the observed dependent variable and x beta, the observed covariance. So the error term is a function of the y vector. Now we assume the likelihood, or the joint distribution rather, for the error term, but we need the joint distribution for the dependent variable. And to get from one to the other, we use the concept of a Jacobian of the transformation. That's a general concept that has to do with transformations of variables that have a functional relationship between each other, and specifically it is the determinant in multivariate settings. It is the determinant of the partial derivative of the functional relationship with respect to the new variable. So it's very important to get this right. So the old variable is a function of the new variable, and we take the partial derivative of that function with respect to the new variable. And for the spatial lag model, this turns out to be the determinant of I minus rho w, an n by n matrix. And we see this by going back to the previous slide. You see the functional form, the f, for E is a function of y, and the only term that changes with y is this matrix in front of it, I minus rho w. So the Jacobian is the result of the application of matrix calculus, and it's a scalar. It's not a matrix, it's a scalar because it's the determinant of the matrix. However, it's a determinant of a matrix of the dimensions of the data set, which is going to create problems for computation. This n by n matrix doesn't go away. So important to remember, we assume the distribution for the error term. We need the log likelihood for the observable and observed dependent variable. There is a functional relationship between the two, and to get the correct likelihood, we need this concept of a Jacobian of the transformation between the new and the old variable. And so this Jacobian then, this scalar, is something that scales up the probability function for the new variable so that it sums to 1, so to speak, so that it integrates to 1. And this Jacobian expression, the determinant of I minus rho w, is a function of the parameter rho. So we can't just, it's not a constant. It changes with rho. So it has to be part of the log likelihood function, which is a non-standard result. If you're familiar with maximum likelihood estimation in a regression context, in a classical regression context, you will not see this Jacobian there. But actually, it is there, but it doesn't matter. If you look at the functional relationship in a standard classical regression, the error term is a function of y minus x beta. So the f function of the transformation is y minus x beta. So taking the partial derivative of this function f with respect to y, the result is 1. So it doesn't matter. It's not present in the likelihood function. So then how do we proceed? We proceed by starting with the likelihood for the error term. We replace the expression for the error term by its functional transformation. In our case, that is y minus rho w y minus x beta. This is what we use to get the Jacobian. And we include the Jacobian term. So if we look at the log likelihood, we again have the first constant term with log of 2 pi, which we can ignore. Then the determinant of the variance-covariance matrix sigma is simplified because of the form sigma squared I. So we get the log of sigma squared, which is a scalar. And then we get the log of the Jacobian term of the determinant of I minus rho w. And then we get the weighted least square, so to speak, which is 1 over 2 sigma squared and the cross product of the error term. So the weighted least squares part is simplified because of the structure of the variance-covariance matrix. So there's two unusual aspects to this log likelihood. One is that it's because of the spatial dependence, it cannot be expressed as a sum of the individual likelihoods, the likelihoods for the individual observations, but it has to be expressed as a joint density for all the observations together. And the second unusual aspect is that the log of the Jacobian determinant is in there as an additional term. So we proceed as usual for maximum likelihood estimation. We have the log likelihood as a function of the parameters, in this case sigma squared, rho, and the vector beta. And we need to find the value for those parameters that maximize the log likelihood function. And we proceed in the usual fashion, first order conditions and then second order conditions. I'll go over this fairly quickly. I'm basically giving this to you as general background just to give a sense of how this works. Fortunately, as it turns out, to maximize the log likelihood with respect to beta and sigma squared, we get analytical solutions that are conditional on a value for the spatial autoregressive parameter rho. So we can express this concisely by replacing the matrix I minus rho w in our notation by the matrix A. And you see this expression for the estimate of the regression coefficients can be computed as a difference between two regression coefficients that can be computed ahead of time, but it is a function of rho. So we can compute the B sub 0 and the BL ahead of time for a given row, we have the regression vector. And similarly, with these two b's in hand, we can compute two error vectors, and then the correct error vector is again a weighted difference between the two of those. This is actually incorrect. It should be E0 minus rho EL prime E0 minus rho EL. I'll correct this later. So then we take the expression for B, which is only a function of rho. We take the expression for sigma squared, and we substitute it into the log likelihood, which gives us the following so-called concentrated likelihood function, or sometimes also called profile likelihood function. So since B and sigma squared are a function of rho, we end up with this expression, which is a function of a single parameter, rho, that we need to maximize. So rho is in this sum of squares, the log of the sum of squares that we see in the first term, and rho is also part of the log of the Jacobian. As it turns out, the parameter space is not the usual -1 to +1, but the parameter space is a function of the structure of the weights matrix. Specifically, the parameter space is constrained by the inverse of the smallest on the real line eigenvalue and the inverse of the largest eigenvalue. So the parameter space depends on the eigenvalues of the spatial weights matrix. As it turns out, for a rho standardized spatial weights matrix, which is typically what we will be using, the largest eigenvalue is 1. So the upper bound for the spatial autoregressive parameter in a situation where the spatial weights matrix is rho standardized will be 1. The lower bound, however, will tend to be more negative than -1. And that really depends on the structure of the weights. So that's the first order condition, which gives us the solution for the parameters. That doesn't give us any inference. If you remember, the inference is based on the information matrix, which is found from the second partial derivatives of the log likelihood function. So we have to figure this out. We have to compute the second order partial derivatives. We have to take its expected value and then the inverse of that. This is a very complicated expression. The usual simplifications don't hold. And just to give you an idea, here's what it looks like. So we see a lot of big matrices in there. The W sub A is W times I minus rho W inverse. That's the inverse of an n by n matrix. And we also see a lot of trace terms in there. You may recall these trace terms from the Lagrange multiplier test statistics. And of course, there is a connection between because the Lagrange multiplier test statistics use this second order partial derivative to set up the statistic. It uses it by setting the value for the spatial parameter to 0. So then the asymptotic variance matrix is the inverse of this. And notice something very unusual. Typically, in a regression model, there is a block structure between the variance of the regression parameter and the variance of the error term. Here, that's not the case. You see this term, the third term on the first row and the bottom term on the first column, precludes the block diagonality of these two parts, the regression part and the error part. In other words, the precision of the spatial parameter is affected by the precision of the error term. This is a very non-standard result and is not the case in classical regression. So how do we get the asymptotic variance matrix then for the lag model? We compute all these elements of this information matrix and we take its inverse. There's no analytic expression for this, but we do know because of the structure of the matrix that it will not be block diagonal between rho and sigma squared. So this is a highly non-standard result, something that highlights the complexity of the spatial autocorrelation embedded in the spatial lag term and embedded in the error term. So to sum it all up, how do we approach maximum likelihood estimation in the spatial lag model? We start by fully specifying the distribution as a multivariate normal distribution for the error term. Then we exploit the functional relationship between the error term and the observed dependent variable to compute a Jacobian of the transformation. That's the determinant of I minus rho w. This allows us to move from the log likelihood for the error term, which is a joint log likelihood, not the sum of the individual elements, to the log likelihood of the dependent variable. And we just substitute the expression for the error term by its form that includes the dependent variable and the regressors. This gives us a log likelihood function of rho, sigma squared, and beta. We take the first partial derivatives to find the values of the parameter that maximize the log likelihood, and we take the second partial derivatives and the inverse of that matrix to have a sense of the precision of these estimates.